Recording is rolling. It is Wednesday, December 4. So let's see, makeup quiz list. Like I'm checking these off. Yeah, I think I gave out all the what they need to give off there. Right. So we're actually for context here, we're a couple minutes into class. Before I hit record, I showed you guys an example of this show and tell opportunity. So if you want to bring something into school or email me a picture that I can put into a PowerPoint that you can talk about, then your opportunity is Friday, December 13th. Could be a show and tell day. We'll do. All right, so agenda today, we're going to finish this momentum half page. We've got about half of it done so far, so we'll do the other half. Turn this in to the grade tray by the end of class. I'm going to grade those to make sure you guys are getting all the correct answers. And then about the last 20 minutes of class or so will be a coefficient of restitution lab. You guys probably see some bouncy balls around and some meter sticks. And that's all you need. Ball and a meter stick and some paper. You can calculate coefficient of restitution. So you can leave it there. All right. Okay, so you guys get with the agenda what we're doing. All right. So we of course are doing momentum. You guys remember momentum is mass times velocity. It's a vector. It's conserved in collisions. Right. Here's a real basic collision. These are all head-on collisions we're doing. So we've got two objects, say along the x-axis, bam, right flag, and then what? Well, maybe they stick together, maybe they bounce off, but regardless of how they bounce off, this is always true. If you add up the mass times velocity bits before and after the collision, they always have to equate. And actually, that is a perfect one right there for one that we have not done in class yet. Do you guys see number 4? Number 4? So let's do that right now. Let's do number 4. This one's just a general conservation of momentum. Okay. Oh, yeah. Oh, all right. So number 4. Okay. All right. It says, okay, two objects measure masses. Okay, so I gave you the masses, collide head on, pow, resulting in these given measurements. Right? What was the initial velocity of, say, object B, which is the only number I did not give you? So you know how fast object A was going before, and you know post-collision how fast they're going, and also what direction. You guys see some positive and negative values, right? Possibly. There is a little bit different numbers, but so maybe sort of a realistic type scenario for this might be something like this. Suppose you're a forensic investigator one day, and maybe there's been some car collision, and you're looking at the tread marks on the ground, saying, "Okay, well, I see after the collision how fast each car must have been going because I can see the tread marks, kind of how they were moving, and I know the mass of the car, so that's not too hard to get." Right? And we have some security video footage, so I can see like at the edge of the video like one car in motion, so I see how fast that was going. But what was the other car doing? Was he speeding? Was he doing something he wasn't supposed to be doing? I don't. Hey, wait! I know conservation of momentum, so I can solve that. We can solve that exactly what we're going to do right here. And so here's your framework: sum of momentum before the collision equals sum of momentum after the collision. Right. So momentum, of course, is mass times velocity, mass A, velocity A initial, plus mass B, velocity B initial. I'm saying plus because that's the sum of. Then equals mass A, velocity A final, plus mass B, velocity B final. Right? So there's your framework right there. Okay. Ooh, while you guys are getting up to that point, hey guys, why am I putting arrows above, say, this P and above the V's? What does the arrow mean? It means it's a what kind of quantity? A vector. A vector. So direction matters. Something's going right or left that is important to momentum, right? If it's positive or negative type motion. All right, so let's see, I'm going to do something times something plus something times something equals something times something plus something times something. Right, so it's going to look like this. Okay. I should have given you most of these numbers. So I'm working off my page. I know the masses on my page are 1 kilogram, which shows up here and here, versus 1.3 kilograms, which shows up here and here. Okay, so I got my masses. I know after the collision, this looks like -3 meters per second versus positive 4 meters per second. So maybe there's some kind of like rebound type motion because after the collision, it looks like they're traveling like this. Right? What about before the collision? Before the collision, I know, where is it? Velocity A initial, right here, right, is going this many meters per second. Right. Oh, and that is a positive value. So I see before the collision, maybe this was heading positive, and then after the collision, it's going negative. Okay, yeah, so definitely some kind of boing, some kind of like that. But what is this VB initial? How fast was object B going before the collision? Of course, since momentum is conserved, we can solve that. All right, you guys get that? All right. So here, throw in the middle step. I see 6 kilogram meter per second of momentum right there. Okay. I got whatever 1.3 kilograms times this unknown velocity is here. Solve for. Okay. That's going to result in what is all this right here? Let's see. -3 plus 1.3 times 4. Okay. Looking at 2.2 kilogram meter per second of momentum. Okay. So at least on my paper with my numbers, I have this much momentum in the system, which means that there was always that much because this is a closed system. So that's also true before. And I can finish this with algebra. All I have to do is subtract this over and then divide by this coefficient mass right here. Okay. So BBO is this many kilogram meter per second minus this many kilogram meter per second, all divided by this mass in kilograms. Right. BBO is, let's see, this many meters per second. Right? The fact that it's negative, that tells me something too. That tells me it was traveling in the negative direction leading up to the collision. Right? Yeah, so probably looks just about like this. Boing, something like that. Do it again. Boing. Probably it. Right? Now, while you guys are finishing that one, I'm going to do one more check on these numbers. Okay? I'm interested, this is not on the page, but I'm interested in what is the kinetic energy before the collision? What is the kinetic energy after the collision? So I have to add up the 1/2 mv squared. Isn't that kinetic energy? 1/2 mv squared? Let's try it. So 1/2 times this m times this v squared plus 1/2 times this m times what we just solved, v squared. Okay. Put it all together. I'm saying before the collision, there were 23.5 joules of kinetic energy. Okay. Yeah, if I do the same thing after the collision, I do all these post-collision values. Right? Who can tell me? What am I going to get for kinetic energy? Is it going to be more than, less than, or equal to 23.5 joules? Right. Well, it might be equal to, but only if it's perfectly elastic. So maybe, but probably not. If it's not perfectly elastic, it's got to be what? Which would be more than, less than 23 joules. Yeah, less than, right? Right. Kinetic energy is probably going to go down unless it's perfectly elastic. Then it might say, well, let's see. So 1/2 times m times this v squared plus 1/2 times this m times this v squared is 14.9 joules. It did go down. It did go down. Right, you guys see that? Right. Here's a kind of obscure side thought. If you are ever a physics teacher yourself one day and you're just making up problems on the fly, be careful because if conservation of momentum, it's kind of hard to tell what came first and what came last. But if you do a kinetic energy check, you know for sure. Okay, this came first because there's more kinetic energy. And this is post-collision because what? Okay, that's it. All right. So everybody good on number 4? Okay, all right, so that's a good warm-up puzzle because that's right in line with what we've been doing this week. All right, so I think at this point we've covered 1 through 5. Have we finished 1 through 5? All right, well, all right. On the back side, yeah, true. We did finish 6 and 7 the other day. So 6 is the explosion, 7 is the elastic collision. We did those, right? We just got these last 4 right here. 8, 9, 10, 11. Right, you guys ready? So now 8, 9, I'm gonna come back to because that's the lab I'm gonna have you guys do later today. Right, so we'll come back to those. But number 10 and 11, 10 and 11. Right, you guys ready for 10 and 11? So these are impulse questions. Now, if you were here yesterday, I think I covered this poster, but it's worth seeing a second time. And if you weren't maybe testing, then, well, here you go. So suppose you maybe hit a ball with a bat, which is actually the premise on number 10 and 11. They both say you hit a ball with a bat. Right? Oh, well, that's definitely a collision of some kind, right? You would definitely be changing the velocity of the ball, right? By changing the momentum of the ball, right? So how do you get a change in momentum? That's what delta P is. You guys see delta P, change in momentum? Okay. You get that by applying a force for some time interval, force times time. And in class yesterday, here, this is a page from yesterday, we were looking at the units to see, does that make sense in terms of units? mass times velocity, it'd be kilogram meter per second, force times time. It ended up being the same units. Right? Newtons times seconds is the same units. Okay. Right. So apply force for some time, it'll change the momentum. Right. And if you ever see this graph, it'd be force versus time. And guys, what property of the graph is that? What property of the graph? Is a coordinate, a slope, or an area? It's the area under the curve, isn't it? Right. In fact, this kind of reminds me of, this looks a lot like, you guys remember work was force times distance? Work was force times distance. If you saw a force versus distance graph, the energy transferred, which is work, was the area under that curve, right? This is a really similar idea, right? Like an adjacent idea, right? So force versus time. Okay. Now, if I'm hitting this ball with this bat, oftentimes you see triangle-looking curves for these type graphs. Here's why, right? Because if you film this in slow motion, guys, this collision, do you think this collision happens in like a few milliseconds, maybe a few milliseconds? Right? Yeah, really, really tiny time interval, like bam, happens so fast, right? Right. What's gonna happen is this ball's gonna come in and first make contact with the bat right about here. Then the bat pushes against the ball. And finally, the ball starts to reverse direction right about here. Right? Now the ball's going the other way. And finally, the ball leaves contact with the bat here. So if you film that in slow motion and watch frame by frame, then and put that together like force versus time, it might look, approximately like that. And these usually do. They don't have to. You can find an average force, like if this was an iceberg and it melted down to this average force value, right? Or maybe you're just like pushing something over a few seconds, could be, right? But oftentimes these are like a fraction of a second, and you get triangle-looking curves. Don't have to, but you usually do. Okay? Right. All right. So let's try this out. Right. Number 10. A bat hits a baseball with some given amount of time, and I told you the force, and I told you the mass of the baseball. What is the change in velocity for the baseball? What is the baseball's change in velocity? All right, so number 10, mass times change in velocity, which we're solving for, comes from applying a force. It's really an average force, if you want a hard number on that, for some time interval. Okay. Well, I told you the mass of the baseball. Pop that in right there. Right, change in velocity, we're solving for. Okay. And I told you the average force of the bat on the ball. Right, so my number on my paper is this many newtons right here. And it should be a tiny time interval. I think it would make sense. Well, right? One algebra step. All I have to do is divide down the mass, right? Divide down the mass. I'll get a change in velocity is, let's try this out. So that many newtons times that many seconds. Okay, so there's the impulse, right? Divide by the mass that's acting on. It tells me the change of velocity is 42 meters per second. All right. Do you guys get your change of velocity also? It's a number on your paper. It's all working out. Okay, you guys got that? Okay, so this should answer the question on the paper. But all right, I got a side question for you guys. What does that mean? So let's do a few of these. What if the ball started out on a tee? So the ball's just sitting there at rest on a tee. And then you come along with the bat and bam, hit the ball. Right. Guys, how fast does that ball leave that tee? How fast? 42 meters per second. Well, if you have my numbers, that would be right. How about this? Let's not have the ball on the tee. What if a pitcher throws the ball at 21 meters per second towards the plate? Right. And then the bat, bam, slaps that ball back the other way. Right. Now, let's say it's all the same numbers, the same force and time of the same ball. Right. Guys, if you pitch the ball to the left at 21 meters per second, and you have a change in velocity of 42 meters per second, how fast does that ball go back towards the right? Careful. There's a sneaky hidden negative sign there, because to the left, to the right, you're hitting it to the right. The ball was going to the left. What is negative 21 plus 42? Positive 21 to the right. Guys, it's like this. Your final velocity could be equal to your initial velocity plus the change in velocity. Does that make sense? Right? Whatever you start with plus the change is what you end up with. Right? So here I've got negative 21 meters per second plus 42 meters per second is the change. Gives me positive 21 meters per second. You guys see that? Okay. Let's do one more of these. What if the pitcher throws a changeup? and it comes in at 10 meters per second to the left. And all same numbers, pow, pow, bat, pow, to the right. How fast is that ball being kicked back to the right? 32 meters per second. Yeah, there you go. Right. Another way to think of this is a change in velocity could be final velocity minus initial velocity. Right. So it's the same thing, just rearranged. Right. So if you have 32 meters per second left to bat minus the negative 10 meters per second that was headed towards the plate, don't forget the negative. So I'm subtracting a negative. That brings me back to positive 42 meters per second, which is the change, which is what we got from impulse. Okay. All right. So how fast does the ball leave the bat? Well, it really depends on how fast the pitcher pushed it towards the plate to begin with. So you could have a bajillion different answers. Okay. Right, guys, that? Right. So really, with this method, you're just solving for the change. Right. Right, you guys ready for number 11? Number 11. Right. So number 11, same premise. Hit a baseball with a bat. Same baseball mass, blah, blah, blah. Right. This time I'm asking, what is the average force? So same setup, number 11. So average force, which is a vector, times time interval results in some mass times change of velocity. Okay. I want to know, what is this average force right here? Okay. We got about the same time interval, tiny number of seconds. Got the same baseball, so many kilograms. Right. And I gave you a change in velocity. Now my change in velocity is, looks like this many meters per second right here. So, guys saw it? Okay. All right, so one algebra step. All I have to do is divide this time over. Ooh. Guys, take a look at this. Kilograms, I'm looking at the units, right? Kilograms times meters per second divided by seconds. Kilogram times meters per second divided by seconds. That's kilogram meter per second squared, right? Guys, what is that unit equal to? 1 Newton, right? 1 Newton is 1 kilogram meter per second squared. Isn't that like F equals ma, force equals mass times acceleration? Yeah. Actually, a lot of teachers teach it that way. They say, oh, this impulse formula right here is just one step away from Newton's second law of motion. Divide the time interval down, same thing. Right, so let's get a hard number on this. What is that mass ball times that change in velocity divided by the time that happened in? Okay. I'm getting an average force of this many newtons right here. All right. Are you guys also getting an average force value on your paper? You guys got that? All right. Everybody good? Pretty good. All right. Again, I have an extension question for you guys. So what does that mean in context? Here, let's put that answer next to this graph, because the question I have, the graph is going to help to answer this. Okay. Suppose this baseball was sewed together with kind of weak thread, and the threads can handle up to, 300 newtons. As long as you hit it with less than 300 newtons, the ball is safe, it's all intact, it's all good to go. But if you hit this baseball with more than 300 newtons, the seams are all going to bust apart and you got a busted baseball. So, guys, take a look at my example numbers right here. Is my baseball safe? Is it going to stay intact, or is it going to bust all apart? Let me see. Show of hands. How many guys think that this baseball, you guys remember it busts at 300 newtons, right? How many guys think that this baseball is safe and it stays together? How many guys think it gets all busted up and the seams fall apart? Ooh, I think the seams would fall apart. Here's why. Guys, what type of force is this? This is a what type of force? What's the subscript say? Average force, right? Now, if it was a constant force, then that would be also true. The constant force would be the average force, and it would be like a flat line, and then the area in the curve would be a rectangle. That'd be all good to go. But I said that's not normally how this plays out. Normally, it's actually like a triangle graph, right? So if the average force right here is 220 newtons, do you guys see what the maximum force probably is during that collision? Which would be how much? 440 newtons. You guys see that? Right? So, yeah, so that's why I think this baseball is going to bust apart. Okay. You guys get that? All right. Everybody good with 10 and 11? All right. All right. So the only two we have left on this page are number 8 and number 9. Number 8 and 9. And these are both coefficient of restitution questions. So what is coefficient of restitution? This is a way you can quantify how bouncy is a collision. You guys remember a collision that could be like the whole spectrum of collisions? Like on one end of the spectrum, you got perfectly inelastic where they stick together. And on the other end, you could have perfectly bouncy, they boing, right? Bounce off as well as they could ever bounce, right? But really, it's a spectrum. So realistically, like for this, it's probably somewhere in the middle, right? That's not perfectly either one, right? Right. So how can you quantify how bouncy is a collision? So here's the physics term for that, and a way you can quantify that: coefficient of restitution. Okay. Oh, here, side note: since I'm making a video for all my classes, I tell my AP students AP does not ask about this, so this is not going to be on the AP exam, right? So that aside, oh, all you need to do is say, what's the post-collision difference in velocities? Post-collision difference in velocities compared to, so divided by, the pre-collision difference in velocities, right? And that's it. Right? Notice you don't actually need the masses of the objects to solve this, right? To solve how bouncy is something. So let's try this out. There's a little bit more to it, but I'm gonna save that for after solving this. So number eight, right? So coefficient of restitution is, okay, I got my fraction set up. Let me just start writing. Let's say I'm trying to remember this from scratch. Well, I know it's a ratio of differences in velocities. What's the difference after compared to before? That might be something maybe like this: velocity of object B post collision minus velocity of object A post collision. Right, like vectors, right? Vectors, right? Be careful about vectors. If the direction is changing, you might have positive and negative numbers. Watch for that. Okay? And then velocity of B before the collision minus velocity of A before the collision. Okay, maybe something like that. Okay. And tell you what, I actually am missing one little detail. This is not 100% correct. There's one little detail that's off. Okay. All right, but I want to kind of lead into this, see if you guys can figure this out. Okay. So, because if you have a collision and two objects bounce off each other, isn't it true they're gonna maybe oftentimes reverse direction, right? Like boing, reverse direction, they could, right? And if they do that, if you ran this at face value, exactly as I wrote it, turns out you'll always end up with a negative value because of that reason. This will always be negative, right? Which, if it's always negative, that's maybe kind of annoying to work with. So could you just make it always positive? Right? And guys, if a number is always negative and you want it to be more simply a positive number, how can you make it a positive number? What's one way to do it? Absolute value. Boom. I've thrown some absolute value bars, right? Another way to do it is you can just slap a negative sign in front, right? A lot of physics textbooks, they just throw a negative sign right there, right? And a third way you can do it, and what I did on this poster, is actually, if you look real close, how many guys caught actually reversed the balls? Do you guys notice that? On top I got, here you go. Longer the school. On top I got B minus A. On bottom, I got A minus B. You guys catch that? A little detail, but that's another way to do it. All right, so a little bit tricky. All right. All right. Oh, how about this? Do you guys remember from last couple of days? What's the smallest number this could ever possibly be? 0. That's if they stick together. Then they would not be moving relative to each other. The numerator would be 0, so the whole thing's 0. What's the biggest this number could ever be? 1. Yeah, if it's perfectly elastic, boing, like Newton's cradle. Yeah, this could go up to like 1.00. Right, so let's put some numbers in here. Velocity B after I've got what is that right? Yeah, it's got a -2 meters per second there. Velocity A post collision, got 3 meters per second there. B before. Ooh, looks like this one started at rest. B right there. And then A before got, ooh, right. So I have negatives flying all over. Actually, I should kind of rewrite this. So negative, got -2, -3, all divided by 0 minus -9. Guys, if you subtract a negative, does that same thing as plus a positive? Okay. Right. And then on top, looks like this negative and this negative cancel. So is that like 5/9, I think, on my paper? 5, 6. I think my numbers work it out about like that. Okay. Right. What that means is this. When the two objects were headed towards each other, there was some difference in velocities. After they bounce off each other, the difference in velocities is only 56% as much, at least with my numbers. Okay. All right, get that? right, here we got number 8. You guys ready for number 9? All right. Now, number 9 is also a coefficient of restitution question, but it's a special scenario. It's you're bouncing a ball off the floor. Okay. Guys, if you bounce a ball off the floor, this is about to be your lab in a few minutes, by the way, so focus attention to this one. If you bounce a ball off the floor, what are the two objects that are colliding with each other? The ball and the what? The earth. Yeah, the ball and the earth, or you say the ball and the floor. Okay. The earth, the floor, not moving. Guys, if you bounce this ball against the earth, does the earth move a little bit? Maybe like a tiny fraction of an atom, but basically not. And then when the ball bounces back up, gravitational forces just pull back together, so it cancels out anyway. We're going to say that the earth is not moving due to this collision. Okay? I mean, that probably makes sense, right? Right. So the difference in velocity between the ball and the floor is just the velocity of the ball, because the earth will just call 0 meters per second. Right? Right. So if I want to know the coefficient of restitution of the ball, say against the tile floor, right, some kind of material properties, ball point bounce, right, I need to get what's the rebound speed compared to the crash speed. Okay. Guys, which speed is faster, the rebound speed or the crash speed? I think the crash speed is going to be a little faster, right? Right. However fast it lands, it's going to rebound maybe a little slower, right? Something like that. Okay. Oh, dang it! I didn't give you guys any speed gates. I gave you guys meter sticks. Can you guys calculate these speeds based on these heights, the drop height and the rebound height? How can you do that? I got it covered up right here. I got it covered up. Guys, what is speed based on height? What is that? Square root 2gh. You guys remember the Galileo question, conservation of energy? We derived that. Or if you go way back in the day, you could actually pick this third kinematic formula and also derive it that way too. Right? And square root 2gh is what it is. Right? So since you guys have seen that so many times, I just went ahead and wrote that here. And then you can feed each of these square root expressions into rebound speed versus crash speed. Right? Ooh, guys, is the 2g gonna cancel? Right? And now you have two different heights, rebound versus drop height. So those are different. Right? And you still got the square root. So it's this answer right here. It's the square root of the ratio of the heights. Okay, guess that? So that's exactly what we're gonna do. Solve this on paper. So number 9, coefficient of restitution is square root of rebound height compared to drop height. Okay. So plug in my numbers. I have a rebound height of, oh, there's my rebound height, there's my drop height in meters. If I take square root of that, I'm going to get about this ratio right here. Okay. And now what that means is this. When this ball is coming down, about to hit the ground, it's going some speed. When it rebounds, boing, it's going 71% of that crash speed. The rebound speed is 71% of the crash speed for this particular ball. Okay. Right, guys, it. All right. And you guys got yours too? It's all working out. All right. You guys ready for a lab? There should be is there a blank half page on your desk? You guys got a blank half page? All right. And if you don't, there might be some on these desks somewhere around. Go ahead and find a blank half page. Okay. And I'm going to have you guys do, well, pretty much what we just did. Oh, I meant to mention, you guys turned in this momentum half page to the grade tray before you walk out of class today. So turn in this page to the grade tray before you walk out of class, and I'm going to grade that and give you guys some points in the grade book. Right. Now, this lab, go ahead and copy down this table. What I want you guys to do is pick one ball. So pick your favorite ball. Could be this one, this one, this one. Just pick your favorite ball. Should be a bunch of balls going around. Okay. And try different drop heights. So here's your drop height. Maybe you could do 100 centimeters, then like 80 centimeters and 60 centimeters and 40 centimeters. So try different drop heights and measure with the meter stick how high does it rebound to for each of those drop heights, and then calculate coefficient of restitution. And one more thing, I want you guys to graph rebound height versus drop height. When you guys have both the table and the graph, then I will check that off and give you guys lab points, okay? And in the grade book. Okay. So earlier today, some students wanted to see an example of a graph. So here, I'll show you guys. Okay. So you're doing rebound height versus drop height. So here's my rebound height. Now I did mine in meters. If you want to do centimeters, that's perfectly fine too. Okay. And here's drop height. Again, I did meters. Guys, where does your graph start at the origin? Is what? 0, 0. Is your graph going to start at 0, 0? Yes. Do all graphs in this class start at 0, 0? Yes, they do. Yeah, in this class, start at 0, 0. Okay. And then are you going to scale this linearly? Like, for example, 20, 40, 60, 80, 100 centimeters you could do. And the same thing here, 20, 40, 60, 80, 100 centimeters, right? Okay. So your graph's going to start at 0, 0. You're going to scale it linearly. And then you're going to take numbers from this table. Hey, are these like XY coordinates right here? XY coordinates, right? You can plot them, point, point, point. I wonder what that graph is going to look like. Huh? What's that graph going to look like? Right. Well, you're going to know in a few minutes here. Right. So go ahead. Once you got a table and you have that graph, then I will check that off, give you points. And also remember to turn that momentum half page into the gray tray.